Hello everyone. Thank you for having interest in my presentation. My name is Jehyun Lee from Trustwave. Today, I'm going to talk to you about our phishing email detection system named the Defense, that is a flexible ensemble of machine random detection models. The phishing emails are our starting point of many attacks like information filtration and malware infection. Thus, they are a serious security concern for an organization, especially to an enterprise. Against the phishing emails, there have been many technical improvements and proposals utilizing the machine learning and deep learning techniques, but most of those techniques target only a specific email component, such as email text, email header, or URL in the email. Our proposal is to build a multimodal detection system with the sophisticated detection models to cover each different email component and compose them to cooperatively make the final decision. Our evaluation with near 300,000 of email collected from real-world enterprises, our system, named the Defense, achieves over 99% legal rate at 10 to minus fourth of positive rate. Let me start from our motivation. An email is a composition of multiple components, like email header, readable plain text, HTML, and URL. Because each component has different functionality and semantics, a detection model likely relies on a specific component. But in practice, phishing emails and attackers in the wild are very diverse, and each model for a single component is easily evadable by the attack vectors targeting the other components. For example, email header analysis is evadable by sending an email through a very normal email services. On the other hand, text analysis is evadable by the emails without any text but only an image. This is inherent even to the techniques which cover over 99% of phishing emails in the wild. We found that most of the phishing emails have either of HTML and URL or both. But in spite of the good coverage, detection only with the HTML or URL does not achieve sufficient accuracy. I'll show this in our evaluation. From the limitations in coverage and accuracy, we propose Defense, a flexible phishing email detection system with multiple analysis modules. Defense has three individual detection modules. First, structure module for the email headers and HTML structures. Text module for the readable text in the plain text and also in HTML. Lastly, URL module for the embedded URLs in the emails. The strengths of Defense are in 3 points. First, it has wide email component coverage and is easy to extend the modules. Each module is independent to the others in its decision process, and the predictions of individual modules are weighted and aggregated by the Meta-classifier. Secondly, Defense is designed for standalone solution to achieve high accuracy without any help of external information sources. Lastly, in practical operation of Defense, a user has a room for flexibly tune the model configuration and update. Let me introduce these three modules and Meta-classifier one by one. Structure module analyzes the email headers and HTML sections with tens of the features. Some of the features came from previous source, and we added novel features inspired from our observation on recent phishing emails. The features are modeled by supervised learning algorithms like random forest, SVM, and XGBoost. In the text module, we adapt BERT, short-up bidirectional encoder representations from transformers, which is a well-known pre-trained language representation. But unlike the generative use cases in the other fields, we use BERT as a vectorization method, and the vectors are used as the feature set of supervised learning. So it allows to replace the BERT with any other method which converts a text sentence into a numeric vector. The URL module only works with the URL strings without visiting the URL. We use deep learning approach to run the URL strings. We use CNN LSTM architecture for URL string classification that models abstraction of set of characters in convolution layers and also sequences of the abstracted units in LSTM. For the final decision, we use a Meta-classifier which is trained from the individual modules' prediction values. The Meta-classifier runs the correlation and conditional weights of the individual modules from supervised learning. For example, if individual modules have different accuracies in different prediction values, the model for Meta-classifier runs the prediction value ranges with the labels. Let me move to the evaluation of Defense. We tested defense with near 300,000 unique email samples collected from multiple enterprises. The ground truth labels are first detected by multiple commercial solutions and finally reviewed by the recipients of the emails. We split the dataset into three subsets: training set for individual modules, training set for the meta-classifier, and the test set. I want to highlight our performance metric in the evaluation. In practical operation of phishing email detection solutions, the low false positive is a very critical factor in the user's business. Even if there is a sweet spot in the trade-off between false negative and false positive, a user usually wants to guarantee of the low false positive. Therefore, we use the recall at a fixed false positive as the main performance metric for comparison. First, selected the models for each module. From the detection performance, we picked one model for the best accuracy without regarding time consumption, and we took two models to find the cost-efficient configurations by tuning their parameters. We compared defense with single model solutions proposed in the previous work and without our novel structural features. We measured the area on the precision recall curve, AUPRC, and recall at 0.201 false positive rate from 10 cross-fault validation with the enterprise email dataset. In a recall at 10 to minus third, that is 0.1% false positive rate, defense shows better and stable accuracy with less standard deviation. The random forest model with our new structure features at the first row of the table also shows the similar performance to defense, but the gap becomes larger when you set a lower FPL. At a very strict false positive rate, 10 to the minus fourth, defense contributes to detect the missing phishing emails by the structure module. Text module and URL module do not have good performance alone compared to the structure module, but they are clearly contributing to 4% more recall, which makes missing of 1,000 phishing emails in our test dataset. Beyond the accuracy, we found efficient feature and modeling configurations for each module. First, in the structure module, the most time-consuming task is the feature extraction. We observed that feature extraction time is mainly affected by the headers, fields, and strings the module reads and parses. So we categorized the features into 10 categories and tested the combinations. And yes, there were the combinations that do not have much loss in recall, but has more than 40% smaller feature extraction time. For the URL module, where CNN STM shows the best accuracy, we compared the hyperparameters like the numbers of units in each layer and running epoch. It is straightforward that less iteration of running rounds and higher pooling size take shorter training time. We measured the performance of defense from the combinations of individual module configurations. We tested different feature sets for structure module, dim running hyperparameters for URL module, and the numbers of words for text module. In the plots, we fixed the text module configuration to use only first 100 words. Because there was very small difference in recall when it decreased the numbers of words to 100 while the time consumption decreased significantly. The x-axis of plot is training and testing time, and the y-axis is the recall. The purple points are the recall at 10 to the minus 4th FPL for each combination, and green points are for 10 to the minus 5th FPL. From the result, we can confirm our expectation here that with the reduced features and simpler deep learning models, we still achieve 95% of recall at the 10 to the minus 5th FPL. Let me conclude my presentation. Defense is a flexible and modularized phishing email detection system that widely covers email components. Powered by the composition of multiple modules, Defense achieves high performance, in particular, higher recall than the previous works and our individual modules at very low false positive. When we use computationally heavy features and deep learning techniques, it comes with high time consumption in training and testing. But we found that synergistic configurations allow to use reduced features and lightweight models without losing detection accuracy. This is the end of my presentation, and thank you for your attention. I would be happy to hear your comments and questions. Thank you.